1880s, Northeast America. Steam hissed through iron pipes as building owners demanded central heat without explosions. European engineers arrived with thin, lightweight radiators promising speed and efficiency. American foundries were casting thick sectional iron in sand molds, running low-pressure steam systems that European visitors called too slow, too crude, too heavy. Through the smoke of Pennsylvania foundries, Nelson Bundy was threading together cast iron sections like Lincoln logs. Each piece weighed 25 pounds empty. Each held over 2 liters of water. European sheet metal radiators weighed half as much and heated rooms faster. Industry experts insisted the future belonged to lightweight aluminum panels with quick response times and modern controls. But something was happening in those heavy American radiators that the efficiency consultants never measured. Something about chemistry, something about time, something that would keep rooms warm in the Dakota building for over 140 years, while modern aluminum systems failed with pinhole leaks in 15. The Americans weren't building radiators. They were building thermal batteries that would outlast every innovation that came after them. The foundry floor at American Radiator Company's Buffalo Works rang with the steady percussion of sand tampers and the whoosh of molten iron hitting packed molds. It was 1892, and Nelson Bundy walked between the casting lines with the measured pace of a man who understood that precision came from patience, not speed. The European delegation visiting that morning had already voiced their skepticism about American methods. Too heavy, they said. Too slow to respond to changing room temperatures. Too crude for the refined heating systems that London and Paris demanded. Bundy paused beside a freshly cast radiator section, its gray iron surface still radiating heat from the pour. The piece measured 5 millimeters thick at minimum, often reaching 8 millimeters in the heaviest sections. When empty, it weighed 11 kilograms. When filled with water for operation, it would hold nearly 3 liters and tip the scales at 14 kilograms per section. A typical room installation required 12 to 15 sections, creating a thermal mass that European engineers found incomprehensible. The visiting delegation from Birmingham clustered around a display of English sheet metal radiators, their thin walls gleaming with modern efficiency. These units heated rooms in minutes rather than the slow, steady warmth that American cast iron provided. The lead engineer, a precise man named Whitmore, gestured toward the lightweight panels with obvious pride. "Gentlemen, observe the mathematics of heat transfer. Thin walls, rapid response, minimal water content. Our radiators achieve temperature equilibrium in under 10 minutes. Bundy nodded politely but kept his attention on the sand molds being prepared for the next pour. Each mold required careful packing around wooden patterns that had been refined through dozens of iterations. The process was deliberately slow, allowing the molten iron to fill every detail of the pattern and create the internal waterways that would carry steam through the finished section. This was not mass production in the European sense of stamping and welding thin sheets. This was precision casting that prioritized durability over speed. John Pierce emerged from the company offices carrying a sheaf of installation reports from New York and Boston. As co-founder of Pierce Steam Heating before the merger, he had spent 2 decades watching American heating systems operate in conditions that would challenge any European design. The Northeast winters were brutal, building construction was often hasty, and maintenance was frequently delayed until systems failed completely. European radiators, with their emphasis on quick response and lightweight construction, simply did not survive these conditions. "Mr. Whitmore," Pierce said, approaching the English delegation, "your radiators are indeed efficient in controlled conditions, but observe these failure reports from mixed metal installations in Boston." He handed over a folder containing photographs of pinhole leaks in aluminum panels that had been installed alongside existing copper and steel piping. "The chemistry of our water systems is not as predictable as your laboratory conditions suggest." The European engineer examined the photographs with growing concern. The aluminum radiators showed clear signs of galvanic corrosion, where dissimilar metals had created electrical couples in the presence of treated municipal water. The pH levels that protected steel and iron components had pushed aluminum beyond its narrow comfort zone, resulting in localized pitting that penetrated the thin walls within 5 to 7 years of installation. Bundy seized the moment to explain the American approach. "We cast thick walls because chemistry doesn't negotiate," he said, running his hand along the substantial iron section. "When iron operates in deoxygenated hot water systems, it forms a magnetite layer. This protective film actually slows further corrosion. But aluminum requires precise pH control that becomes impractical when copper fittings and steel pipes are present in the same loop." The foundry supervisor called for the next pour, and the delegation watched as workers maneuvered a crucible of molten iron toward the waiting molds. The temperature reached 2,800 degrees Fahrenheit, hot enough to fill every detail of the pattern while maintaining the slow cooling rate that produced the dense, strong castings American systems demanded. This was not the quick production cycle that European factories preferred, but it created radiators that could operate reliably for decades without the water chemistry management that thin wall systems required. Pierce produced another set of documents, these showing pressure specifications for American steam systems. "European practice runs steam at higher pressures for faster heat distribution," he explained. "American systems operate at 2 pounds per square inch gauge or lower. At 2 psig, saturated steam reaches 218 degrees Fahrenheit, hot enough for effective heating, gentle enough to avoid the mechanical stress that can cause failures in thin wall components." The mathematics of thermal mass became clear as Bundy explained the operational differences. A typical cast iron radiator section held nearly 3 liters of water along with the substantial metal mass of the iron itself. Gray cast iron stored approximately 35% more heat per liter than aluminum construction, and the additional water content created a thermal battery that continued radiating heat even after the boiler cycled off. This meant fewer starts and stops for the heating plant, reduced mechanical wear, and steady room temperatures that occupants found more comfortable than the rapid temperature swings of quick-response systems. Whitmore examined the specifications with professional interest, despite his obvious preference for European methods. The American approach required more installation labor due to the weight of individual sections, and the slow thermal response meant that room temperatures took longer to adjust when heating demands changed. But the durability figures were undeniable. American Radiator Company was providing 20-year warranties on cast iron installations, while European manufacturers typically limited coverage to 5 years due to the corrosion risks inherent in thin-wall mixed metal systems. As the morning progressed and the delegation prepared to return to their hotel, Bundy made one final demonstration. He led them to a test installation where identical rooms were heated by American cast iron and English sheet metal radiators. Both systems had been shut down simultaneously 30 minutes earlier. The room with European radiators had already dropped 8 degrees Fahrenheit. The cast iron installation showed a temperature decrease of only 3 degrees, the massive thermal storage continuing to release heat long after the steam supply ended. "Build it heavy, run it light," Bundy said as the visitors departed. "The iron remembers the heat even when the fire forgets." By 1895, the philosophical divide between American mass and European speed had crystallized into competing technical doctrines that would shape heating systems for the next century. In Detroit, the newly expanded American Radiator Company factories were producing cast iron sections according to specifications that seemed almost defiant of modern efficiency trends. Each section maintained minimum wall thickness of 5 millimeters, often reaching 8 millimeters in load-bearing areas, while European manufacturers were perfecting aluminum die casting techniques that achieved functional walls as thin as 1.5 millimeters. Clarence Woolley stood in the company's engineering offices reviewing comparative heat output calculations that laid bare the fundamental disagreement between the two approaches. European aluminum radiators could achieve identical heat transfer ratings with 60% less metal and 40% less water content than American cast iron designs. The mathematics were indisputable when measured purely in terms of immediate response to temperature changes. An aluminum panel radiator could bring a cold room to comfortable temperature in 12 minutes. The equivalent cast iron installation required 38 minutes to reach the same room temperature. But Woolley had learned to read beyond the immediate numbers after reviewing failure reports from mixed installations across the Northeast. The aluminum radiators that responded so quickly to heating demands also surrendered their heat just as rapidly when the boiler cycled off. Room temperatures in aluminum-heated spaces could swing 6 degrees Fahrenheit during normal boiler cycling, creating the thermostat hunting that building operators found maddening. Cast iron installations showed temperature variations of less than 2 degrees during the same cycling periods. The volumetric heat capacity calculations revealed the mechanism behind this stability. Aluminum possessed a specific heat capacity of 900 joules per kilogram per degree Kelvin, but its low density of 2.7 grams per cubic centimeter limited its thermal storage per unit volume. Gray cast iron registered lower specific heat at 460 to 590 joules per kilogram per degree Kelvin, but its density of 7.1 to 7.5 grams per cubic centimeter meant that each liter of cast iron could store approximately 35% more heat than the same volume of aluminum. The water content difference amplified this thermal storage advantage dramatically. A typical cast iron radiator section held 2.9 liters of water in addition to its substantial metal mass. European aluminum panels were designed with internal water volumes as low as 0.8 liters per equivalent heat output rating, prioritizing quick response over thermal storage. American installations regularly included 12 to 18 cast iron sections per room, creating water storage of 35 to 52 liters per radiator. The thermal mass of this combined metal and water created what engineers were beginning to recognize as a thermal battery that could maintain room comfort during extended boiler-off cycles. John Pierce had commissioned side-by-side testing installations in Buffalo office buildings to document these performance differences with actual occupant comfort data. The European-style aluminum installations achieved design temperature quickly, but generated comfort complaints during cold snaps when heating loads peaked and boiler cycling became irregular. Occupants reported feeling alternately overheated and chilled as the lightweight radiators tracked every fluctuation in steam supply. The cast iron installations in comparable rooms maintained steady comfort even when boiler maintenance created extended off periods. The morning reports from Pierce's test installations included detailed temperature logging that quantified the thermal storage effect. After a controlled boiler shutdown, aluminum radiators lost 50% of their heat output within 15 minutes. Cast iron sections continued providing measurable heat for 45 minutes after steam supply ended. Their massive thermal storage releasing energy at a rate that kept rooms comfortable until boiler operation resumed. This thermal flywheel effect meant that cast iron installations could operate with longer boiler cycles, reducing fuel consumption and mechanical wear while maintaining superior occupant comfort. European manufacturers had responded to American thermal storage advantages by developing more sophisticated control systems that could modulate aluminum radiator output to minimize temperature swings. These controls required precise water temperature regulation, motorized valves, and electronic sensors that added significant complexity and cost to installations. American cast iron systems achieved superior temperature stability through passive thermal mass, requiring only simple pressure controls and manual radiator valves. The economic implications were becoming clear as Woolley analyzed installation and maintenance costs across both approaches. European aluminum systems required lower initial labor costs due to their reduced weight, but their control complexity demanded skilled technicians for commissioning and ongoing maintenance. The pH-sensitive nature of aluminum in mixed metal systems necessitated water chemistry management that many building operators found challenging to maintain consistently. Cast iron installations demanded higher initial labor investment due to section weights that often required 2 workers for safe handling, but their operational simplicity meant that building superintendents could maintain them with basic mechanical skills. The robust chemistry tolerance of cast iron systems allowed them to operate reliably with minimal water treatment in the mixed metal installations that were standard in American commercial buildings. A telling example emerged from the Dakota apartment building installation, where original cast iron radiators installed in 1884 continued operating without major maintenance or chemistry management 15 years later. The building superintendent reported that the radiators had never required repair beyond occasional valve packing replacement, and occupant comfort remained excellent despite the building's original boiler being replaced twice during the same period. European aluminum installations of similar vintage showed a different maintenance pattern. Early aluminum radiators in Boston mixed metal systems had begun developing pinhole leaks by their 8th year of operation, particularly in sections where copper fittings created galvanic couples in the presence of treated municipal water. The thin walls that enabled rapid thermal response also meant that minor corrosion represented a larger percentage of total wall thickness, creating leak risks that thick cast iron walls could absorb without functional compromise. Pierce commissioned a metallurgical analysis of failed aluminum sections to understand the corrosion mechanisms that were puzzling European engineers. The reports showed localized pitting corrosion that penetrated 1.5 millimeter walls completely while leaving surrounding areas apparently unaffected. The same corrosive conditions that created surface oxidation on 8 millimeter cast iron walls represented total wall penetration on thin aluminum construction. As 1896 approached, Woolley recognized that American cast iron radiator doctrine was not simply competing with European aluminum efficiency on technical specifications. The American approach represented a fundamentally different philosophy of building systems design, prioritizing long-term durability and operational simplicity over immediate response and control precision. The thermal mass that European engineers dismissed as inefficient was revealing itself as the key to comfort stability that no amount of control sophistication could replicate in lightweight systems. The question was whether American building owners would value this long-term stability over the immediate appeal of quick response and lower installation weight that European systems promised. The chemistry laboratory at Stevens Institute of Technology had become an unlikely battleground for radiator design philosophy by 1897. Professor William Henderson had agreed to investigate the growing reports of premature failures in aluminum heating systems after receiving funding from both American Radiator Company and European manufacturers who insisted their products were being improperly installed. What Henderson discovered in his systematic analysis would fundamentally challenge the assumptions that had driven the lightweight radiator revolution. The first breakthrough came from examining water samples from failed aluminum installations across New York and Boston. Henderson's assistant, Margaret Walsh, had developed a methodical approach to documenting the exact chemistry conditions present when aluminum radiators developed the pinhole leaks that were becoming increasingly common in mixed metal systems. Her meticulous records showed that aluminum failures clustered around specific pH ranges and metal combinations that European manufacturers had not anticipated in their laboratory testing. Henderson's experiments revealed the mechanism that American foundry workers had observed empirically but never fully understood. When cast iron operated in closed hot water systems with minimal oxygen exposure, the iron surfaces naturally formed a tight adherent layer of magnetite, the black iron oxide with the chemical formula Fe3O4. This magnetite film acted as a barrier that actually slowed further corrosion, creating a self-protecting system that improved with age rather than degrading. The magnetite formation process required specific conditions that American low-pressure steam systems naturally provided. Operating temperatures between 210 and 220 degrees Fahrenheit, combined with the deoxygenated environment of a properly sealed steam system, created ideal conditions for stable magnetite layer development. The thick walls of cast iron radiators provided abundant iron for this protective film formation while maintaining structural integrity even if some base metal was consumed in the process. Aluminum presented an entirely different chemical challenge that European engineers had underestimated. Walsh's controlled experiments demonstrated that aluminum required pH levels between 7 and 8.5 to maintain stable oxide films, but the presence of copper fittings and steel piping in typical American installations created galvanic couples that disrupted these protective layers. When pH levels rose above 8.5, which commonly occurred with the lime-based water treatments used to protect steel boilers, aluminum oxide films became unstable and allowed localized attack that penetrated thin walls rapidly. The galvanic corrosion mechanism was particularly devastating to aluminum radiators in mixed metal systems. Henderson's laboratory setup replicated the electrical potential differences that occurred when aluminum sections were connected to copper or steel fittings through the conductive path of treated water. The aluminum acted as an anode in these galvanic couples, literally dissolving to provide electrons that protected the copper and steel components. In thick-walled cast iron systems, similar galvanic effects occurred slowly and were limited by the protective magnetite layers. In thin-walled aluminum construction, the same electrochemical processes could penetrate walls completely within 5 to 8 years. Municipal water chemistry compounded these problems in ways that European manufacturers had not anticipated. American cities were increasingly adding chlorine compounds for water treatment, and these chlorides accelerated the localized pitting that Henderson observed in his test samples. Chloride ions concentrated at aluminum surface irregularities and created conditions for accelerated attack that European laboratory testing with distilled water had never revealed. Walsh documented the progression of aluminum radiator failure with photographic evidence that made the chemistry visible. Initial installations showed bright, uniform aluminum surfaces with excellent heat transfer characteristics. After 3 years of operation in mixed metal systems, microscopic examination revealed the beginning of localized pitting at locations where chloride concentrations had created breakdown points in the protective oxide films. By year 5, these pits had progressed to visible surface irregularities. By years 7 to 9, the pits had penetrated the 1.5 to 2 millimeter walls completely, creating the pinhole leaks that were forcing premature replacement of entire radiator installations. Henderson's analysis of cast iron samples from systems of similar age showed a dramatically different corrosion pattern. The magnetite layers had actually thickened over time, creating increasingly effective protection for the underlying iron. Surface examination revealed minor general corrosion that had consumed perhaps 0.5 millimeter of material from 8 millimeter walls over 15 years of operation. At this rate, cast iron radiators could operate for centuries without structural compromise, while aluminum installations were showing wall penetration in less than a decade. The European response to these findings focused on water treatment as the solution to aluminum's chemistry challenges. Representatives from Birmingham manufacturers argued that proper pH control and conductivity management could extend aluminum radiator life indefinitely. But Henderson's practical analysis revealed the fatal flaw in this approach. American heating systems typically combined radiators with existing boilers, piping, and fittings that had been selected and installed over years or decades. Optimizing water chemistry for aluminum protection often conflicted with the requirements for protecting steel boilers and copper piping. The German VDI 2035 standard, which was emerging as European best practice for closed-loop water quality, acknowledged this fundamental conflict. The standard warned that maintaining optimal pH for aluminum in systems containing copper and steel was likely unfeasible, and recommended using demineralized water with very low conductivity as the only practical approach to preventing galvanic corrosion. But demineralized water systems required ongoing monitoring and makeup water treatment that most American building operations were not equipped to provide. Henderson's final laboratory demonstration crystallized the chemistry advantage that American cast iron systems possessed. He constructed side-by-side test loops containing both aluminum and cast iron heat exchangers, connected to copper fittings and steel piping identical to typical American installations. Both systems used identical water treatment designed to protect steel boilers. After 18 months of accelerated testing at elevated temperatures, the aluminum section showed clear signs of pitting corrosion, while the cast iron sections had developed protective magnetite layers that actually improved their corrosion resistance. The implications extended beyond individual radiator failure to system-wide reliability. When aluminum radiators developed leaks, the resulting water damage often exceeded the cost of the radiators themselves. Cast iron installations that developed minor leaks typically showed warning signs through gradual seepage that allowed planned maintenance rather than emergency repairs. The robust construction that European engineers dismissed as overbuilt provided failure modes that were manageable rather than catastrophic. Margaret Walsh's comprehensive report, documented warranty patterns that confirmed the laboratory findings. European aluminum radiator manufacturers typically provided warranties of 5 to 10 years, with careful exclusions for installations involving mixed metals or improper water chemistry. American cast iron manufacturers were offering 20-year warranties with minimal exclusions, confident that their products would continue operating reliably in real-world conditions that would challenge any lightweight alternative. The chemistry was not negotiating with engineering fashion or efficiency theories. Iron's natural tendency to form protective oxide layers in hot water systems made it inherently compatible with the mixed metal installations that American buildings required, while aluminum's narrow chemistry tolerance made long-term reliability dependent on maintenance precision that most building operators could not sustain consistently. The efficiency revolution had arrived at the Meridian office complex in Lower Manhattan by 2012, bringing with it the promise of reduced energy consumption and precise temperature control that building owners found irresistible. Project manager David Chen stood in the basement mechanical room examining the original 1898 cast iron radiators that had heated the building reliably for over a century. The retrofit proposal spread across his makeshift desk called for complete replacement with European aluminum panel radiators that would reduce the building's thermal mass by 70% and provide zone-by-zone temperature control through electronic thermostatic valves. The environmental consultant, Sarah Martinez, had prepared a compelling presentation showing potential energy savings of 22% through the elimination of thermal lag that kept rooms overheated during mild weather. The new aluminum radiators would respond to temperature changes within minutes, rather than the gradual adjustment that cast iron systems provided. Advanced controls would modulate each radiator based on occupancy sensors and outdoor temperature compensation, creating the kind of precision that green building certification programs rewarded with valuable points and tax incentives. Chen had operated enough building systems to appreciate the appeal of quick response and precise control, but he also understood the complexity that came with sophisticated heating systems. The existing cast iron installation operated with simple manual valves and a single boiler control that had required minimal maintenance over decades of operation. The proposed aluminum system would introduce electronic controls, motorized valves, water treatment equipment, and monitoring systems that would transform the mechanical room from a simple steam plant into something resembling a chemical processing facility. The retrofit proceeded according to schedule through the summer of 2013. Crews removed the original cast iron radiators, each section requiring 2 workers due to their substantial weight. The replacement aluminum panels were light enough for single-person installation, significantly reducing labor costs and installation time. The new radiators looked sleek and modern compared to the utilitarian appearance of the iron sections, and their slim profiles freed up valuable floor space that tenants immediately appreciated. Martinez had specified a comprehensive water treatment system designed to protect the aluminum radiators from the chemistry challenges that had plagued earlier mixed metal installations. The system included pH adjustment equipment, corrosion inhibitor dosing pumps, and conductivity monitoring that would maintain water quality within the narrow parameters that aluminum required for long-term reliability. The existing copper and steel piping would remain, but the water treatment would be optimized to prevent the galvanic corrosion that had caused failures in less sophisticated installations. The system performed impressively during its first heating season. Room temperatures responded quickly to thermostat adjustments, and the building's energy consumption dropped by 18% compared to the previous year with cast iron radiators. Tenants appreciated the ability to adjust temperatures in individual offices, and the building management company featured the retrofit in marketing materials as an example of their commitment to environmental responsibility and tenant comfort. But the water chemistry that looked manageable on engineering drawings proved challenging to maintain in practice. The pH levels required to protect aluminum conflicted with the inhibitor chemistry needed for the existing steel boiler and copper piping. The building's water treatment contractor, Robert Kowalski, found himself constantly adjusting chemical dosing to balance competing requirements. When pH dropped below 7.5 to protect the copper piping, the aluminum radiators showed signs of surface attack. When pH rose above 8.5 to optimize aluminum protection, the steel boiler developed scaling problems that reduced efficiency and required frequent cleaning, The monitoring system generated alarms with increasing frequency as the second heating season progressed. Conductivity levels fluctuated with makeup water additions, and the automatic dosing system struggled to maintain stable conditions. Kowalski documented his growing concerns in monthly reports that showed the system operating outside optimal parameters for aluminum protection approximately 30% of the time. The thin walls of the aluminum radiators left little margin for error when chemistry excursions occurred. By 2015, the first pinhole leaks appeared in radiator sections located in areas where water circulation was poorest and chemistry control most difficult. The leaks started as weeping that stained ceiling tiles and wall surfaces, then progressed to active dripping that required emergency repairs. Chen discovered that individual aluminum panels could not be repaired effectively, requiring complete replacement of failed sections. The modular design that had made installation quick also made partial repairs impossible when corrosion penetrated the thin walls. The failure pattern followed the localized pitting progression that laboratory studies had predicted. Chloride ions from the municipal water supply concentrated at surface irregularities in the aluminum, creating galvanic cells that accelerated attack at specific locations while leaving surrounding areas apparently unaffected. The 1.8 millimeter wall thickness that provided excellent heat transfer characteristics offered minimal resistance once pitting corrosion initiated. Within 18 months of the first visible leaks, 12 radiator panels required complete replacement. Martinez conducted a comprehensive analysis of the system chemistry data to understand why the water treatment had not prevented the failures. Her report revealed that maintaining optimal pH for aluminum protection was indeed impractical in the mixed metal system. The copper fittings required pH below 8 to prevent cupric oxide formation, while the steel boiler needed alkaline conditions above 8.5 to prevent scaling. The aluminum radiators needed pH between 7.5 and 8.5, but the system's complex chemistry interactions made it impossible to maintain stable conditions within this narrow range. The German VDI 2035 standard that Martinez had referenced during system design contained warnings that she had underestimated during the planning phase. The standard specifically cautioned that aluminum in mixed metal systems was prone to pitting corrosion and recommended very low conductivity water as the only practical approach to preventing galvanic effects. But maintaining demineralized water in a large commercial system required continuous monitoring and treatment that the building's operating budget could not support. Chen calculated the total cost of the aluminum radiator failures and found that replacement expenses had already exceeded 20% of the original retrofit investment. The failed panels had caused water damage to office areas that added additional repair costs beyond the mechanical system itself. Meanwhile, he discovered that the original 1898 cast iron radiators that had been removed were still functioning perfectly in the salvage yard where they had been sold. The building that purchased them reported excellent performance and no maintenance requirements beyond occasional valve adjustments. The environmental benefits of the aluminum system were also proving less significant than projected. The energy savings had diminished as failed radiators were bypassed pending replacement, and the complex control system required constant adjustment to maintain occupant comfort. The original cast iron system had provided steady temperatures with minimal energy waste, while the aluminum installation consumed significant electrical power for pumps, controls, and monitoring equipment that the simple steam system had never required. By 2017, Chen faced the possibility of complete radiator replacement less than 5 years after the original retrofit. The aluminum system that had promised decades of efficient operation was showing systematic failures that no amount of water treatment refinement seemed capable of preventing. The chemistry was winning the argument against engineering optimism, just as it had in countless installations where thin walls and mixed metals had created conditions that aluminum could not survive. The irony was not lost on building operators throughout Manhattan who were discovering that the century-old cast iron radiators they had discarded were still heating buildings reliably, while their modern replacements required constant attention and frequent repair. The efficiency revolution had delivered sophisticated controls and quick response, but it had also introduced failure modes that the simple mass of iron had never experienced. Dan Holohan received the call from David Chen, on a gray February morning in 2018, another building manager wrestling with failed aluminum radiators and wondering if the old ways might have been better after all. The Meridian office complex had become a textbook case of modern efficiency meeting 19th century chemistry, and Chen needed someone who understood both the promise of new technology and the proven performance of cast iron systems that had heated American buildings for over a century. Holohan arrived at the Meridian building carrying his pressure gauge, thermometer, and the kind of practical knowledge that came from decades of diagnosing heating systems that had been modified, upgraded, and optimized beyond their original design parameters. The building's mechanical room told the familiar story of complexity layered upon simplicity, with electronic controls and chemical treatment systems surrounding the basic boiler and piping that had once operated with nothing more than a pressure gauge and a manual damper. Chen led him through the building's heating history, from the original 1898 cast iron installation through the 2013 retrofit that had promised energy savings and precise control. The aluminum radiators that remained operational were providing adequate heat, but the ongoing failures and water damage had convinced building ownership that the retrofit had been a costly mistake. The question now was whether to continue replacing failed aluminum panels or return to the cast iron approach that had worked reliably for over a century. The basement storage area still contained 6 of the original cast iron radiator sections that had been too damaged during removal to sell for salvage. Holohan examined these sections with the appreciation of someone who understood the engineering logic behind their substantial construction. Each section showed the 8mm wall thickness that provided thermal mass and corrosion resistance, along with the internal water passages that held nearly 3 liters per section. The magnetite coating that had formed during decades of operation was still intact, creating the protective layer that had prevented the kind of pitting failures that plagued thin aluminum construction. Holohan's inspection revealed that the building's fundamental heating infrastructure remained sound. The original steam mains, returns, and near-boiler piping had been designed for the low-pressure operation that cast iron radiators required. The retrofit to aluminum had necessitated conversion to hot water distribution with pumps and controls, but the underlying piping network could easily support a return to steam operation with properly sized cast iron radiators. The demonstration that Holohan arranged would prove the thermal storage advantage that American engineers had understood since the 1880s. He convinced Chen to install one of the salvageable cast iron sections alongside an equivalent aluminum panel in comparable office spaces, both connected to the building's existing hot water system. The comparison would measure not just heat output, but the comfort characteristics that occupants actually experienced during normal building operation. The side-by-side installation revealed the fundamental difference between thermal mass and quick response. When the building's automated controls called for heat, the aluminum radiator brought its office space to the target temperature in 11 minutes. The cast iron section required 28 minutes to achieve the same room temperature, but when the controls shut off the heat supply, the performance reversed dramatically. The aluminum radiator's output dropped by 50% within 12 minutes, causing room temperature to decline rapidly. The cast iron section continued providing measurable heat for 37 minutes after the water supply ended, its thermal mass releasing stored energy that maintained comfortable conditions. Building occupants in the cast iron-heated office reported steady comfort throughout the day, while the aluminum-heated space generated complaints about temperature swings and drafts as the radiator cycled between full output and rapid cooldown. The thermal flywheel effect that Nelson Bundy had designed into sectional cast iron radiators was still providing superior comfort over a century after his original patents, despite all the advances in controls and monitoring technology. Holohan documented the pressure requirements that made cast iron systems inherently more reliable than their modern alternatives. The original steam system had operated at 12 ounces per square inch, creating saturated steam at 212 degrees Fahrenheit. This low pressure minimized mechanical stress on all system components while providing temperatures hot enough for effective heat transfer. Modern aluminum systems required precise water temperature control and higher pressures to achieve comparable heat output from their reduced thermal mass. The water chemistry analysis that Holohan commissioned confirmed what building operators had learned through painful experience. Cast iron systems created their own protective environment through magnetite formation, while aluminum required constant chemistry management to prevent the galvanic corrosion that had caused the Meridian building's ongoing failures. The robust chemistry tolerance of cast iron meant that buildings could operate with minimal water treatment, while aluminum demanded the kind of precision monitoring that few building maintenance departments were equipped to provide consistently. Chen's cost analysis revealed the economic reality behind the technical performance differences. The original cast iron radiators had operated for 115 years with maintenance limited to occasional valve repacking and paint touch-up. Total maintenance cost over the system's lifetime had been less than $3,000. The aluminum retrofit had cost $240,000 initially and required an additional $87,000 in replacement panels and water damage repairs during its 5-year service life. The environmental calculations were equally revealing. The energy savings from aluminum's quick response characteristics had been offset by the electrical consumption of pumps, controls, and monitoring equipment that cast iron systems did not require. The embedded energy cost of manufacturing replacement aluminum panels every 5 to 10 years exceeded the lifetime energy consumption of cast iron radiators that could operate for centuries without replacement. Holohan's final recommendation drew on both engineering fundamentals and practical building operations experience. The Meridian building should return to cast iron radiators sized for the building's actual heat loads, operate them with low-pressure steam distribution, and eliminate the complex water treatment and control systems that aluminum required. The thermal mass that modern efficiency experts dismissed as wasteful was actually the key to comfort and reliability that no amount of electronic sophistication could replicate. The installation of reclaimed cast iron radiators began in the spring of 2019, with sections sourced from building demolitions and radiator restoration companies that had emerged to serve the growing market of buildings returning to proven technology. Each section was pressure-tested, repainted, and fitted with modern steam vents designed for quiet operation and precise air elimination. The Dakota apartment building, 6 blocks north of the Meridian complex, provided the ultimate proof of cast iron radiator longevity. The original 1884 installation continued heating apartments with the same radiator sections that had been installed when Chester Arthur was president. Building staff reported that the radiators had never required major maintenance, operated silently at pressures measured in ounces rather than pounds, and provided the kind of steady comfort that residents had come to expect from their century-old heating system. As Holohan walked through the Dakota's basement mechanical areas, examining steam mains and radiator connections that predated electric lighting, he reflected on the engineering wisdom that American foundry workers had embedded in cast iron systems. The heavy walls, low pressures, and simple controls that European efficiency experts had dismissed as primitive had created heating systems that outlasted every innovation designed to replace them. The numbers had never lied, but it had taken over a century for building operators to read them correctly.